All right, so as I was saying in the last video, this is basically the discovery of Hubble, what's called Hubble's law. We'll actually see the equation in just a second, but you can actually derive the equation. It's actually not hard here. Once you know it's the velocity is plotted on the vertical axis and the distance to a galaxy. So the velocity is basically the redshift of the galaxy, is plotted on the vertical axis, and the distance to the galaxy is plotted on the horizontal axis. And so you get a straight line, right? I mean, there's some error in here, but there's the straight line, and that is what Hubble's great discovery was, right? And so it actually can be seen very easily in this equation, where the velocity of a galaxy, or this is also known, this is actually better described as the recession velocity. So we often call this the recession velocity, is equal to a constant, which is just the slope of this line, times the distance, right? So times the distance to the galaxy. The slope is called Hubble's constant. It has a value, the modern value is about 70, somewhere between 70 and 71, and the units are kilometers per second per megaparsec, right? And that's, and I'll explain what those units mean. So basically it means that the galaxies are moving, as you can see from this slope, the galaxies are moving faster and faster the further away you get. So every million parsecs. So if you look on this axis right here, there's a million parsecs. There's 2 million parsecs. So every million parsecs, the galaxies are moving twice the speed that they were. Right, and see, you gotta now. The thing about this is you gotta think about this in 3 dimensions, right? So you look out into the universe, right, and just imagine a sphere around you, and that's the really strange part. Every single galaxy that's exactly a million parsecs away from you. So in any direction, right, you go a million parsecs away. So remember, the other thing about this is well outside of the local group. You're talking about really distant galaxies now, um, and so you're a million parsecs away, and every single galaxy is traveling at the same speed, at exactly the same speed, right? Now that should seem strange, right? And what gets even stranger, what the next thing that Hubble noticed, of course, is so if you go out 2 million parsecs, the galaxies are traveling at twice the velocity, right? So that's even odder. That's very strange. And then it continues, of course. Now that this is about the limit of what Hubble could do with the technology that he has, but he had back in the 1920s. But of course, telescopes have gotten a lot better since the Wilson telescope north of Los Angeles, which, by the way, I think I said this already, it's not even used anymore, or it's hardly ever used because the light pollution from Los Angeles is so incredibly is so great that you can't even use that famous telescope that Hubble made this great discovery with. At any rate, so what Hubble ultimately finds is that this is the explanation, right? The universe is simply not that organized. Like if you think about it, you go out a million parsecs, you're not going to have every single galaxy traveling exactly at the same speed. Or you go out 2 million parsecs and every galaxy is traveling at twice that or other, that original speed. And of course there's galaxies in between, that and they also obey this equation, right? And so Hubble right away thought that this seemed odd, and that like I said, the universe is not that organized. So what you're observing is not I repeat, not the velocity of individual galaxies. That's the key. All right, that is Hubble's great discovery, is that this velocity, the thing that you're actually observing, is the expansion of space itself. Okay, so let me repeat that so you all kind of get that in your minds, is that it's the expansion of the universe itself. That's what you're observing. You go out far enough, and galaxies will all be redshifted, and the further away they are, the greater the redshift, and it exactly follows this equation. Right, so that was Hubble's great discovery. It basically proved that the universe has been expanding since the time of the Big Bang. All right. Another thing is, of course, we really wanted to measure this H sub zero very, very accurately. During Hubble's time and the decades after, this value wasn't known very well. Like the actual number. Like I said before, we understand now that it's 70, it's somewhere between 70 and 71 kilometers per second per megaparsec. All right, so every million parsecs, things are moving at 70 kilometers per second faster. But that value, I mean, even when I started college, that value was not as well known. In fact, we knew that it was somewhere between it's somewhere between about 50 kilometers per second per megaparsec, all the way up to 100 kilometers per second per megaparsec. So the value was not very well known, and it took really modern equipment, modern accuracy in the experimental method to really narrow down what this value is. And the reason that this is so important to us is if you figure out what H sub zero is, its units actually turn out to be time. So if you take 1 over H sub zero, the reciprocal of H sub zero, that turns out to be the age of the universe in seconds. And then, of course, you can convert it to years. And that's one of the ways that we figured out that the universe is it's between 13.7 and 13.8 billion years old. Right? So that's a really critical number to establish. All right. So this is another way of looking at it, and this is a really good way. Is imagine making some dots. You take a little magic marker and you make these dots on the surface of a balloon, and you begin to blow up the balloon. Right now, the surface of a balloon, of course, is it's a two-dimensional surface in a three-dimensional world, right? And so you're blowing up this balloon, and so if you imagine, like, let's say that this is the Milky Way. Okay, so right where I have the cursor pointed, that's the Milky Way. So galaxies that are in this direction are traveling at a certain speed. They have a certain redshift. And then galaxies that are the same distance away in a different direction have the exact same redshift. All right. And then let's say, so remember, this is us. And so then if there's a galaxy that's twice as far away, it's moving twice as fast as this one. And the same thing, let's say that this doesn't look like it's quite the same distance, but let's say that this galaxy is twice the distance from this from the Milky Way as this galaxy, this nearer one. If this was twice the distance, this would be traveling twice the speed, and so forth. Right? That's the idea of Hubble's law, is that it's not the individual galaxies that are moving. It is the universe expanding, like the surface of a balloon. Right? That's the basic idea. All right, so that is that was, and by the way, it's not like Hubble came up with this in in 1929, and all of a sudden every scientist on the planet jumped on board and said, "Yeah, he's right." There was other evidence. It took about 50 more years for people to fully accept that Hubble was onto something, and in fact, like I said, this equation is one of the greatest discoveries of all time. And yet Hubble never won a Nobel Prize for this. He certainly should have, but he passed away um, before this was fully accepted by the scientific community. But by the 1960s, there was just absolutely clear evidence that Hubble was right, that the universe is expanding, and we're gonna look at that evidence right now. All right, so um, Hubble's law has to do with the expansion of the universe. All right, yeah, they got that one right. So the Big Bang Theory says that our universe began in this explosion. So the moment of the explosion. Okay, so I'll describe a little bit about what we know about this now from a modern perspective. Is that so the one thing, if you just kind of think about this picture for a second, right? It's kind of hard to actually picture this because um, it's as though it's like it's there like the moment of the Big Bang. There is no out here, right? Everything that that will ever exist, all space, all matter, all time, all energy, is right at that one singularity. That one point that's actually very similar to the singularity at the center of a black hole. In fact, that's what the very famous physicist Stephen Hawking, the English guy that he passed away a few years ago. He was the guy that was in the wheelchair that spent a lot of time thinking about these things. He equated the Big Bang. And that was part of his research. He equated the Big Bang to the singularity at the center of a black hole. All right. At any rate, this thing where comes into existence. We don't know exactly how that happens. That there's a lot of room for our we're trying to understand it, but that it's a very difficult thing to understand. How that exactly happened. Anyhow, so all of space begins to comes into being. First space, and it's really really tiny, and there's no stars or anything. There's not even any atoms or anything like that. At first, it's just space and energy, and tremendous amounts of energy, like tremendous amount of energy. And then as space expanded, and it at first it expands in a very nonlinear way, right? With Hubble's law, okay, so go back to Hubble's law. This is a very linear expansion. It expands at a relatively flat rate, right? The value of H sub 0 is roughly 70, right? At the very beginning of the universe, the expansion rate was very very rapid, and and what that does is that rapid expansion allows the universe to cool off, right? It begins to cool off, and then at, um, after about so a little under 400,000 years, so about 400,000 years or so after the Big Bang, there is photons of light, very unbelievably energetic